Welcome to everyone. Um, my goal of this video is to explain the classification of second order partial differential equations. So, partial differential equations. Um, before clarify the classification of second order partial differential equation, let me explain what is the general form of partial second order partial differential equations. So, a definition a partial differential equation is said to be a second order semi-linear PDE. It can be put in the following form. So the standard form is r of x comma y into uxx plus s of x comma y into uxy plus t of x comma y into uyy, which is equal to some function of, let me take capital F, some function of x, y, u, ux and uy. So here u is my dependent variable, x comma y both are independent variables. So this is the semilinearity part comes in the right hand side. So capital F is the function of x, y, u, ux and uy. You can see that in the right hand side there is no semilinearity part. So all the functions r, s, t are functions of x and y, and there is no semilinearity part. The only semilinearity part comes in the right hand side. Okay. So moreover, this form of standard form of equation is known as second order semilinear PDE, that is partial differential equation. Provided the coefficients are variable coefficients r, s, t satisfies r square plus s square plus t square, this sum not equal to 0, where r, s, t are continuous functions of x and y. So also, what is the solution of this kind of equation? So a solution of this kind of equation, that is second order semi-linear PDE. So this is actually second order. So this is the second order general form of second order semi-linear PDE. So what is the solution of this kind of equation? So let me consider this equation as 1. Solution of this equation is of the form we represent the solution of equation 1 by u of x comma y, and this solution must be a regular solution in a domain D, which is subset of R2, that is R2 is nothing but R cross R. So what is a regular solution? So regular solution means the solution must be a C2 function, and as well as the solution satisfies the equation 1. So what is regular solution? A regular solution is a solution which satisfies our equation 1, as well as the solution is somewhat is it's a function. That function satisfies C2 condition. What is C2? C2 is nothing but continuously twice differentiable functions. So C2 of some domain D, right? So what is C2? Continuously twice differentiable function. So that is C2. A regular solution is a C2 function, as well as it satisfies equation 1, right? Suppose I am considering an equation, a linear second order equation, uxx minus utt equal to 0. So here the semilinearity part is 0, right? The coefficient of when compare this equation with the equation 1, the coefficient of the coefficient variable is r is 1 and t is minus 1, and then semilinearity part is 0, right? So it's a linear second order partial differential equation, right? So the solution, suppose I'm taking some function u of x comma t. This is something x plus some t whole square. Let me verify this is a solution or not. So first let me check whether this function satisfies our equation. So ux is, what is ux? 2 into x plus t, and what is that is differentiating this function partially with respect to x. So another notation this for this one is dou u by dou x, and uxx is 2, right? So this is equal to, this is nothing but dou square u by dou x square, that is differentiating the function u with respect to x twice, right? Next ut is 2 into x plus t, and this is nothing but dou u by dou t, and utt is 2, again it is 2, right? So this is nothing but dou square u by dou t square. And now substitute these two terms in our given equation, partial differential equation. So the value is, what is our equation? This is our equation uxx minus utt equal to 0. So substituting this we get 0. So this function satisfies our partial differential equation. So is this a solution of our partial differential equation? Still we have to verify the another condition, that C2, that is whether our function is C2. That is nothing but if it second derivative exists, that is twice it is continuously differentiable, then it is C2. Yes, it is a C2 function. The partial derivatives uxx as well as utt, both values are 2, which means some constant value. We know that the constant function is continuous, so that this solution is u of x comma t equal to x plus t whole square is a C2 function, right? So this is our solution, that is a regular solution for this partial differential equation. Okay, so far we have discussed what is the general form of second order semi-linear PDE, and what is the solution of that PDE, right? So next we discuss the classification of second order PDE, right? Before that, why should we study the second order partial differential equation? So the solution is, the second order partial differential equation occur widely in many other areas of engineering, physics, chemistry, even in mathematics. So the application is broad. So in second order partial differential equation, three types of, so in second order partial differential equations, three types of equations are most important. One is wave equation. Wave equation. So the equation is dou square u by dou x square equal to 1 by c square into dou square u by dou t square. So this is exactly, this is the one dimensional linear second order partial differential equation, right? It is one dimensional wave equation. Why it is one dimensional? Since the spatial coordinates occurred is only one variable, that is x. So here x is the only spatial coordinate and t is the time variable. X is spatial coordinate. So next, second type of equation is heat equation. Heat equation is nothing but dou u by dou t equal to some k into dou square u by dou x square. So here k is, what is k actually? K is some k1 by c rho. Here k1 is nothing but the thermal conductivity. K1 is the thermal conductivity, and rho is rho is the density of a solid, and C is specific heat of the solid. So K1 is thermal conductivity of the solid, C is specific heat of the solid, and rho is the density of the solid, right? So let me recall in wave equation. In wave equation we have used 1 by c square. So what is actually c square? C square is nothing but t by rho. So t is suppose we are considering a string of some particular length. So in a string, the tensions, suppose I'm fixing 2 points in a string. So the t is nothing but the tensions caused at the points P and Q in the horizontal direction. So T is the tensions caused at the points P and Q in the horizontal direction, and rho is the linear density of the string, right? So, and the third equation is Laplace equation. So what is a Laplace equation? The two-dimensional Laplace equation is dou square u by dou x square plus dou square u by dou y square equal to 0. Why it is two-dimensional? Here the spatial coordinates are x and y. Two spatial coordinates are involved, so it's a two-dimensional Laplace equation. And moreover, in heat equation it is also one-dimensional, since the number of spatial coordinates is only one. X is the spatial coordinates and t is time variable. So now we come to our ultimate goal of this video, that is classification of second order PDE. So we classify the second order PDE into three types. Number one, so classification of second order PDE. So we classify second order PDE into three types. One is hyperbolic type, second one is parabolic type, and third one is elliptic type. So how we classify these three types? So at the beginning of this video we have discussed the general form of second order PDE. So this is the equation, general form of second order semilinear PDE. So in that equation R is RST. We are using this RST. Using this RST, if S square provided, the condition is a second order semilinear PDE is said to be hyperbolic type. The condition is S square minus 4RT is greater than 0, and the condition for parabolic type is S square minus 4RT is equal to 0, and for elliptic type the condition is less than 0, right? So these are the classifications of second order PDE, right? So what are the examples of these types? For the first type, let me take the wave equation. In wave equation, actually what is what is the R in wave equation? R value is actually, when you cross multiply this, you get c square, right? So c square, and S value is 0, and so S equal to 0, and T equal to minus 1. So let me rearrange the wave equation. What is wave equation? This is wave equation. So uxx, that is c square uxx minus utt equal to 0, right? So when comparing this with our general form of second order PDE, R value is c square, R is c square, S is 0, and T is minus 1. So calculating S square minus 4RT, this is actually 0 minus 4c square minus 1, so this is 4c square. So this is always greater than 0. So an example for hyperbolic type is wave equation, right? So wave equation is hyperbolic type, and for heat equation, so parabolic type, heat equation is a parabolic type, right? So what is a heat equation? This is heat equation. So similarly we take what is R equal to the K and S T, both are 0. So for wave, this is for a wave equation, and now for heat equation, rt equal to 0, right? So when calculating s square minus 4rt, this is 0 minus 4 into k into 0. So this is 0. So s square minus 4rt is 0. It is, so therefore our heat equation is parabolic type. And for our Laplace equation, so in Laplace equation, what is R? R is 1, s equal to 0, and t is 1. So calculating s square minus 4rt, this is 0 minus 4 into 1 into 1. So this is minus 4. This is always less than 0. So our Laplace equation is of elliptic type. So thank you.